Okay, so we're going to do some problems from the book, and these are exercises 43 through 54, and we're doing a selected number of those. And we're going to use the delta epsilon definition of a limit, where if you give me an arbitrary value of epsilon, or a height above and below my limit point, I can give you a width, or delta, or a half-width, delta, such that every value of the function has to be contained within the box that the half-width forms along with that half-height. So I'm trying to find the limit as x goes to 4 of x plus 2. I try out direct substitution. I take the value that I'm approaching and I directly substitute it into the function and see if I get out something that isn't an undefined value. So if I take 4 and add 2, I get 6, and I claim that this is my value of L. So if I don't know if something is equal or not, I'll put a little question mark above the equal sign. So I have to go through with the delta epsilon version of a limit proof to find that that this is indeed true, that this is indeed the limit that I am looking for. So if x is no more than some delta that I have to find away from 4, that should imply that my function f of x never gets more than epsilon away from my value of L. So I have to show that x plus 2 minus 6, the absolute value of that, has to be less than epsilon for any epsilon that you give me. So if I simplify this, I see that I get the absolute value of x minus 4. Now, if I choose, I have direct control over this, right? I can say how wide my box is. It turns out that the height of my function away from 6 is going to be exactly the width of my function away from 6 if I choose delta equal to epsilon. So if you say epsilon equal to 2, right? So 6 plus 2 is 8 and 6 minus 2 is 4. Then the box would have to be have a width, a half width of 2 as well, right? So our box actually ends up becoming a square. This would actually work if we approached any value of c on the left or right. So instead of just approaching x as it goes to 4, let's approach an arbitrary value of c. And the proof actually ends up becoming something very similar to this one special case of just approaching 4. So I'll replace 4 with c in most of the locations that are shown up here. This is going a little bit above and beyond what the question asks for, but I just wanted to show that what it would look like in the general sense. So if x is no more than delta away from some c value, I need to show that my function f of x is going to be no more than a value of L. And I do a direct substitution again, and whenever I do that direct substitution, I just put in the value of c instead of x, and then this is c plus 2. So as x approaches c, x plus 2 should approach c plus 2. So I put in, I want to show that every value of my function that is in a small interval around this value of c, whatever that might be. In our last example it was 2. It gets no more than, the value of the function gets no more than epsilon away from the limit that I claim. So if I simplify this, I can just drop the parentheses right here, and this just becomes x plus 2. And this negative gets distributed to both terms here. and I see that this plus 2 and this minus 2 cancel, and I come out with something very similar to the case that we had last time, right? When c was equal to a concrete value of 4. Here, I get absolute value of x minus c. So again, the height of our box is equal to the width of our box if we set that. So we again choose delta equal to epsilon. So if c was negative 4 up here and I did all the same work out again, I would find that delta was still equal to epsilon in this case. If c was equal to negative 1, I would do all the work out and I would find the same thing. And if c was equal to 2, that's the example that we did last time, right? So anytime that if you gave me a height of 0.001, my width would also be 0.001 of my box. This means that the limit is actually defined everywhere at each of these points. And I just wanted to show you in this one simple example what that looked like. Next time we're going to do number 44.